want to welcome everyone here to the DSI 101 Technology Fundamentals. The DSUA board members, we kind of had some ongoing discussions and thought that a session like this would be beneficial and helpful. So whether, maybe not everyone could use a 101 course, but given that there's always a lot of new people coming into the industry or always a turnover and someone looking for a refresher or someone that, maybe they want to learn something a little bit more about the fundamentals of the technology that they've got to be responsible for. We thought this would be a helpful recording to have. First, before we kind of get in the meat and potatoes of this, I wanted to acknowledge the DSUA. DSUA sponsors. Our platinum sponsors are Lawas North America, Mississippi Lime Company, Redicam, Integrated Global Services, Gecko Robotics, National Filter Media, RPM Solutions. Our gold sponsors are Noltec, Reaction Analytics Solutions, Primex, US Lime Company, and our silver sponsors are Leckler, Atlas Carbon, and Carton Fujikin. Would definitely like to thank those guys and anyone in the dry scrubbing industry. It's a good mix of whether you got looking for dry scrubbing consumables from sorbents to valves to spray nozzles or filter bags, that's or even dry scrubbing equipment suppliers or any kind of technical services for dry scrubbing, from CFD modeling, performance optimization, anything along the lines of inspection and corrective solutions, for erosion and corrosion problems. All things related to dry scrubbing. Our sponsors are made up of folks that can offer, some technical solutions there. So anyone needs any specific help, happy to put you guys in touch. Send us an email through the DSUA website, and we'll be happy to put you guys in touch with whomever you need. So, thanks to you guys, and thanks to our sponsors. Wanted to get right into this to leave as much time to kind of talk and allow you guys to have as much opportunity to ask questions. We have two speakers today. The first gentleman you see here is Mitch Lund. You guys, if you've been part of the DSUA webinars, you've seen Mitch. He's an account manager at Hafe Equipment, but Mitch has served DSUA for, I think, the past 2 years as an advisor, supporting these webinars in terms of coordination, execution, a lot of stuff in the background. Mitch has been instrumental in helping pull a lot of these together and helping DSUA. Mitch's background, he's a chemical engineer, currently out of the Charlotte, North Carolina area, heading back to Minnesota here pretty soon. He's spent nearly a decade in the air pollution control industry, providing solutions, dry scrubbing solutions, mainly around DSI for acid gas emission control. He also has worked as a technical consultant for dry scrubbing end users, providing, custom solutions for about 3.5 years. And prior to that, he was responsible for all the sales, strategy, and technology innovation in the environmental solutions division of Noltec. And then the other speaker who will be joining us is Dave Luchtenberg. Dave's a principal engineer at AEP. He's been doing process engineering work on both wet and dry scrubbing technologies for the electric generating utility industry since 2008. Dave is AEP's dry sorbent injection subject matter expert, which makes him a great person for this webinar. So AEP has 5 sites with DSI systems, 3 of them for SO3 emission control, 2 of them for SO2 emission control. And Dave was instrumental in being involved in overseeing the installation and startup of all those systems. And currently Dave's a technical lead to retrofit their 3 SO3 control systems to help improve their performance and switch sorbents from trona to hydrated lime. Dave has been around the dry scrubbing industry, even as for those who are familiar with the dry hydrate users group, Dave has been actively participating in that since 2009. That was something that, end users, equipment suppliers, lime suppliers, we got together to ultimately focus on trying to help develop and improve the DSI solution. So, Dave's been actively involved in that. Dave is currently a director for DSUA this year. And you guys are probably familiar with Dave, as he's done a couple webinars last year back in what looks like, I think December. There was a DSI user panel, and he gave a great one on their SO2 emission control and talking about dispersion. So bear with us. We're having, Dave's having a little technical difficulties. So Mitch is going to kick this off, and Dave will be joining us in a timely fashion. The joys of the virtual life that we live, but I'm going to turn it over to Mitch now to get started and take control. But if anyone has any questions, again, as per the usual format, feel free to send them in to us. We'll promptly ask them. This is being recorded, so if you got to hop off or want to share this with someone in the future, once the recording's uploaded to YouTube, we'll send it out to everyone so you can have an opportunity to watch it again. All right, Mitch, take it away.
All right. Well, no, I appreciate the introduction, Jerry. First of all, I should confirm. I got a second monitor here. You guys can see my screen, right? Am I sharing it correctly? You can see the title screen, right, Jerry? Okay. So yeah, as first off, I want to mention that I think since the last webinar we did, if you guys watched the last one I hosted right around Christmas, you probably noticed that I probably have a different look now. So don't be freaked out by the new hairstyle or the new beard. This is still me. So not a trick or anything. But yeah, as Jerry kind of mentioned, my colleague Dave, who helped me put together this presentation, is running into little internet issues. So he's going to be joining us midway. And we'll just roll with the punches like we do with these on the webinars, right? So what we're talking about today is the technology fundamentals for DSI 101. As Jerry kind of mentioned, we thought with our core mission at DSUA, which by the way, I got my DSUA polo on today. Our core mission is to really exchange information and also network our peers in the industry. And certainly we thought having a resource of having these fundamental technology type presentations is helpful for not only the live webinars, but also for archived resources, right? The more things you can look back, presentations, webinars, and watch on your own time to kind of learn yourself and educate yourself. We want to make sure we give you those tools. So that's really the whole point of this. And I think what we want to do, we want to encourage critical thinking and problem solving in this organization. We don't want to use this as a presentation to tell you the answer. We want to share our own experiences, our own observations with some technology principles we see in the industry, with the hopes that if you come across a future problem that you don't know how to solve, at least this is some baseline fundamental knowledge base that you can pull from to help solve the problem specific to your guys' plants or applications. So this is not a Bible, this is merely advice and consultation, if you will. So I want to emphasize that. So kind of just getting right into it, I thought we might just clarify for those that are brand new to this, what is DSI, right? Well, that stands for dry sorbent injection, and it's called all sorts of things. If you're injecting activated carbon, some people might call it carbon injection. If you're injecting lime, it might be called lime injection, sodium injection. There's all sorts of synonyms for it, right? But at the end of the day, the operating principle of all of those types of technologies is that we're injecting dry, usually, alkalis. I know the sodium bisulfate crew might say, oh, that's maybe not entirely true, but fundamentally, we're injecting dry alkalis or bases into flue gas streams to remove acid gases or heavy metal emissions, in the case of mercury, for example, for either environmental compliance or plant operational benefit. Dry sorbent injection at its core is an air pollution control process that always includes the following steps, always. 4 steps. First one is storage. We have to have an area of the process that's storing the sorbent that we're using for injection. And that can be a 50-pound bag, that can be a super sack, that can be a storage silo in bulk storage. But you always have to have some storage local to the process to be able to continually inject into the stream. Second step is metering and feeding. So the rate at which pollutants are moved from the flue gas stream is directly correlated to how much sorbent is being injected into the process. So this is a continuous injection process. And because that's a requirement to keep the technology removing pollutants in the flue gas stream, we have to have a way to continuously feed the sorbent into the flue gas. And there's multiple ways to do that too. Rotary airlocks, loss and weight screw feeders, volumetric screw feeders are some of the more common ones that we'll talk to later. But at the end of the day, you have to have a process that's metering the sorbent into the flue gas stream. The third step is conveying. The area where the sorbent is being stored is typically not immediately local to where we're applying it to the flue gas stream. So there has to be some means of getting it from the metering location to the injection location. How are you getting it from point A to point B? Most applications are pneumatically conveyed. Some are vacuum, if you're close enough. Some are pressure. Some are screw conveyed. Like there's all sorts of way to convey the product from point A to point B. It really depends on the layout of your plant, the layout of your plant. But you have to find a way to move from point A to point B. The last part of the process, once we get to point B, we have to inject into the flue gas duct. So the injection grid is there to connect the dry sorbent with the pollutant for the reaction. This is an acid-based reaction that as soon as a sorbent particle contacts a pollutant particle, it's almost an instantaneous reaction, but we have to find a means to get them to contact each other physically. So every single dry sorbent injection system includes those steps in some way, shape, or form. So showing an example process flow. This is obviously a bulk storage system that is probably more so used for a large utility scale application, but I'll kind of walk through those 4 steps here. So product storage silo shown here. Again, this is a silo system, but I mentioned that this can be a variety of ways that you can store the product, including super sacks. We have our dosing equipment. So this is an example of the metering part of the process that I just went over. So this is, in this case, there's loss and weight weigh vessels that have load cells to them that are metering into the stream with rotary airlocks. The next step here is a motive air and conditioning system. So that's the step 3 of the process, conveying the product from point A to point B. And then lastly, we have our injection grid. So in this situation, we'll get into this a little later. This has a convey line splitter that splits the main convey line from a common trunk line to individual lances. And these lances are the grid that's going to be dispersing product across the duct to again, try to maximize our contact within the flue gas duct. So that's an example of a typical process flow for a dry sorbent injection system. I do want to say and comment that this part of the process here, so one of the biggest, I guess, challenges in the dry sorbent injection world, and anybody that's been in this industry we've been talking about this since we've started doing this, but the idea of efficiently contacting the sorbent particles to the pollutant particles is the holy grail of this industry. It's in the life cycle of a typical dry sorbent injection system. These are high operating expense processes. Finding a way to maximize efficiency of the sorbent you're injecting in the duct is critical and paramount to optimizing your cost of the system. And to give you an idea, that this is from the time that those sorbent particles enter the duct to when they're removed from the process in a bag house or an ESP, you probably only have anywhere from 1 to 5 seconds typically. Some situations have 10, but we have to essentially remove a lot of pollutants in a very short period of time in a relatively large space. I think the analogy that I've kind of heard is that if you envision the duct is the New Orleans Superdome, and you put 1 million ping pong balls in the New Orleans Superdome, try to find the pollutants are on the order of 1,000 ppm, and we have to remove 90% of them. So ultimately, it's trying to take 1,000 of those ping pong balls that are in the New Orleans Superdome and trying to gather them all within a 5-second period. It's a very challenging application when you think about it on a scale basis. Jerry, is there anything you want to add there? I want to make sure I'm getting your sorbent. So I guess I want to also add, me and Dave are equipment guys. So this presentation is going to be focusing on the equipment technology side of things, but I always like to value Jerry's opinion from the sorbent side as well, because they're usually partners in this. So anything you want to comment there, Jerry?
No, I think you're right. I think for especially folks that are new or not aware, that there's just been, between papers, presentations, duct videos. Dave gave a great one with a duct camera video on one of the DSUA webinars, that you really do not want to trivialize the sorbent dispersion. And even as a sorbent supplier, I would comment to say that the concept of dispersion is as critical, if not more critical, than even the sorbent properties themselves, because you can have the best sorbent in the world, but if it doesn't come in contact with the acid gases that are present, it can't react. It's still, we'd like to think that the utility world has probably done a lot of work to understand this better, but this is also geared toward the industrial world. And I still come out to sites and find plants that have a single pipe that goes up to the duct wall and doesn't even go into the center of the gas stream. So there's still a lot of knowledge to be spread out there to people, to really focus on do not undervalue sorbent dispersion and the design of how you plan to get the sorbent dispersed within the ductwork. So just, again, doubling down on the fact that there are papers, there's data, there's videos, there's a lot of information out there, I think, to help educate people. And I think DSUA is happy to help put people in touch with, whether it's some of the webinars or other papers, presentations, or whatever, but there's a lot of good information there, and people just need to be aware of that, because it's super critical to driving down operating costs, because less sorbent in is going to equal less waste generated, and it's all part of the holistic cost associated with the solution.
Yeah, I think that's actually
right.
a good point.
No offense, Jerry, but I was just going to say, I want to use as little of your product as I possibly can. The less of your product that I use, the more effective we're going to be. And that's the truth. And really the absolute number one way to minimize how much product you're using is dispersion. Dispersion is king. There's no doubt about it.
We will definitely be touching on that. And that brings up a good point, is that the sorbent plus the equipment, I mentioned this is an air pollution control process. And if we're looking at, if you respect it as a process, your process is only going to be as good as your weakest link. So whether that's the equipment side, whether it's the sorbent side, it has to be viewed as an entire process. So when you're optimizing it, you focus on the weakest link and try to continually improve, right? So now good additions, Dave and Jerry, thanks for that. Dave, glad to see that we got things figured out. That's awesome. We can hear you loud and clear. That's great. So just continuing on, just again, what is DSI? I mentioned it's a chemical reaction between the alkaline and the acid gas that produces instantaneously, almost, a stable high melting point mineral, like a calcium chloride, for example. That mineral is then removed in the particulate collection device downstream of the injection point, whether it's a fabric filter baghouse, whether that's an electrostatic precipitator, ESP. The melting point, just for context, the melting point of some of these minerals, I think, are in the range of 1300 to 2700 Fahrenheit type of thing. So at any point in the process, it's going to be a solid particle, which is good. And an important reminder, I have to give credit to Haley Turner at LG&E for kind of connecting the dots on this. It's kind of like the light bulb moment for me too. But in any environmental regulations, we have our air emissions, we have our water regulations, we have our ground regulations, if you will, ash regulations, landfills, etc. What we're doing with DSI is we are not removing it entirely from, we can't create or destroy matter, right? We're simply converting it from an air emission particle to a mineral, which is then removed with the fly ash and sent to a landfill or wherever it's going. It's simply converted from air to a different solids, to a different phase, if you will. So in DSI, we're converting that from air emissions to ground emissions. But I think that's important, as again, we can't create or destroy matter. We can only change where it's going, type of thing. So it's not It's not a magic bullet. It seems like magic, but it's not. It's just physics. So pros and cons of this technology, certainly since myself, Dave, and Jerry are subject matter experts in here and probably a little biased, we definitely have more pros than cons with this technology, but I'll just go down the list. This is definitely a more mature, proven technology. I think in the United States, it's, I mean, certainly been around in mass since the early 2000s when kind of the blue plume phenomenon started to happen in the utility industry. And then as people kind of learned more and more about this technology and figured out how other areas it can be applied, you see it all over the place, essentially. It's a lower CapEx investment. I think of alternative technologies, it is the lowest, but wasn't comfortable putting that on the slide, but very low capital investment. You kind of get a flavor for why when you look at the process flow. It's pretty simple, which also is a pro of that. It's a very simple process: storage, meter, convey, and inject. But don't let the simplicity of the process, don't overestimate how difficult some problems that we work to solve actually are. But the process in general is simple. The footprint is small. The installation is flexible. And that really comes down to because we're pneumatically conveying it from a storage, for the most part, pneumatically conveying it from a storage location to an injection location. We're essentially running pipe, which is obviously very flexible where it can be installed. It's very easy to test. What I mean by that is, for people that aren't unfamiliar with DSI, if you want to try it, whether it's for an environmental regulation or an operational benefit, there's trial rigs that can literally be brought to site to emulate the technology in your application before any capital investment is made, which is obviously attractive for a lot of people. It's fuel flexible. I mentioned that metering side of things, ultimately, we're just either ramping up or ramping down the amount of sorbent we're continually injecting into the pipe. So it's not design specific. I mean, of course we design for fuels, but if you want to change fuels, this process is flexible to accommodate either higher or lower amounts of pollutant, or if we want to inject in a different location, like it's easily retrofittable. There's a lot of things that from adaptability that DSI really is good for. The other thing too that I want to highlight is short project schedules. Certainly this is more suitable pre-COVID, but in general, I think from purchasing a system to installing it and having it be up and running, you're talking about a 6 to 12 month project schedule, which compared to alternative technologies is shorter than usual. Some cons, I mentioned the higher OpEx. If you look at the pie of life cycle costs of a DSI system in a 20-25 year period, a huge chunk of it is related to OpEx costs, specifically sorbent costs. And that's just because that's what you're continuously using, right? You're continuously using it 24/7. And that goes back to Dave's point. If you can be more efficient with the system and reduce how impactful that you essentially reduce the overall size of the pie significantly by optimizing your sorbent costs. I will definitely say that poor designs can create maintenance nightmares, certainly early on in the DSI. And even to this day, there are some end users that struggle with these systems on a daily basis. In general, I think the silver lining is that there's usually reasons for that, and they usually come back to optimizing designs and design criteria, which we're going to get to later in the presentation. I also mentioned the relatively inefficiency of this, and that goes back to that spatial challenge of having a pollutant particle find a sorbent particle in a short period of time in a giant space. So if we have to get to those situations where we're removing 95, 96, 98, 99% of pollutants of a high mass loading pollutant like an SO2, the economics of it can get out of control pretty quickly in certain situations. So I think in general, those are I'm about to transition to the technology fundamentals and get into some nitty gritty parts about the actual process. But before I do that, Jerry, Dave, is there anything just from a what is DSI perspective that you guys want to add? Jerry, if you want to go first.
Yeah, Mitch, I think, well, I had a question, but I think just for everyone's sake is, when I think of these cons, the point of this webinar to me is to focus on these cons and how to improve, because like we've already talked about dispersion, like how can we optimize, operating expense? And two, I mean, no system is perfect in that we want you to come away from hopefully lessons learned and experience and consideration so that you can improve the reliability of the systems. Because I know a lot of this is going to be about people that have systems and are trying to figure out how to do those those things. So I think those are two fundamental principles we want to address. One question you mentioned, schedules and COVID, is I think both this for you and Dave, whether it's, and I know Dave's going through his own projects, but are there anything that people should be aware of from whether it's designing a new system, retrofitting a system, or even, aftermarket parts that they may need? Is there anything out there that people should be aware of that is really hard to get right now, or should just from a planning perspective, plan ahead even further than say we would have 2 years ago?
Dave, you want to take that now?
Jerry, I can answer that. So right now we're in the process of procurement on one of our lime conversion projects, and air dehumidifiers are an extra long lead time right now. It's with one vendor in particular, I think it's 32 weeks for delivery. So yeah, well, for one, that speaks to probably how much demand they have on their end, that a lot of people are buying these things. And there's a reason for that. Is dry air is a whole lot better for conveying for a lot of reasons. But getting the moisture out of the air when you're conveying, it really is a really critical step. That's a lesson that was learned the hard way in the industry. When utilities were rolling out their DSI systems, everyone sort of took different tactics, and I don't think anyone dehumidified air up front. And for the folks that were using hydrated lime for the first probably 5 or 6 years, I think they might have regretted their decision because of how much of a pain in the ass it was. It was finally figured out that if you dehumidify the air, a lot of those problems go away. So, to answer your question, yeah, the dehumidifiers are really long lead time right now. And actually a lot of things are, we even found random one-off things are eating our lunch on other projects. On our CCR ELG retrofit going on at Amos, they're having MCCs that are taking 6 months for delivery. Like, we're having to buy refurbished MCCs, things that you wouldn't even consider being a long lead time ever. So, I mean, COVID is sort of a brave new world.
Absolutely. Best way to combat that, just try to stay ahead of the game as much as possible, right? So kind of getting into some technology fundamentals, and we're going to talk about dehumidification later because that is an important one. But right now we're going to start with storage discharging. And I think fundamentally, so if we're thinking about this critically, by design, and this is because of the efficiency aspect, right? We have a very short amount of time to find a sorbent particle and a pollutant particle. And to maximize our chances of doing that, the powders that are used in dry sorbent injection are by design very, very fine. 2 to 50 micron, very common. Some of those are milled. In general, we try to get as much surface area as possible and as much pore volume as possible with these particles. But in general, they're very, very fine. They're not granules, they're powders. And when you have powders that are that fine, they create unique material handling challenges. And certainly one of the material handling challenges we see the most is bin discharging, whether that's in a way hopper or a silo. Two of the most common things we see are material bridging and material rat holing. The diagram that I kind of showed here, show on the screen, kind of illustrates what those look like. I'm sorry if you guys that are watching know exactly what this is, because they can create some pretty bad days at the plant. But why do these happen? And this phenomenon is more and more amplified the finer the particles get. So we have multiple forces working together to make discharging material from these bins as difficult as possible. Ultimately, there's particle to wall forces, there's particle to particle forces. And the finer you get on a microscopic level, you create more opportunity for those finer particles to kind of wedge together like you're seeing on this diagram, I think it's illustrated pretty well. And frankly, when we get moisture incorporated into these particles, it only increases the potential for particle to particle cohesion, which can make bridging and discharging really a pain. So I think in general, there's a few things that the industry does to address this. This is very common really in all bulk handling applications. There's mechanical agitation. There's two types of mechanical agitation. The first one I want to highlight is a high amplitude, low frequency, which is, I actually take that back. I have my slides backwards. So high amplitude, low frequency is kind of like, we call them pneumatic thumpers. So it's kind of simulating the infamous rubber mallet on the side of the hopper. We're doing that. When we're doing that, we're creating high amplitude, low frequency mechanical agitation. And there are devices that you can literally mount to the sides of bins that do that automatically rather than, inducing an operator to do that all the time, which obviously has its own safety and ergonomic risks with that. The other aspect is, and I apologize, I had these mixed up, that's my bad. But the other aspect is low amplitude, high frequency, which is actually like a more common, like a bin vibrator, which is, it's periodically rapidly shakes the bin to induce mechanical flow of the material. So I have a couple pictures here of both. And this one here that is the bin vibrator, an example of one that's attached to the side of a hopper wall. This is a screenshot I took of a video of a pneumatic thumper, literally like every second, just kind of pulsating the bottom of a metal plate there. The other way to induce flow in these bins is pneumatic agitation, which is, in other words, fluidization. That's the idea of injecting a fluid, usually dry compressed air, into the cone of the bin and having that fluidize the particles. And I actually have a clip of applying this to hydrated lime at our facility at Hafe, just to kind of show like these particles, when you pneumatically agitate them, they truly act like a liquid. And let me just show you this video here when I start it. But this at the bottom here, we have a pneumatic agitating cone that's going to inject compressed air, and just watch how this fluid moves once it's induced with a small amount of compressed air. It literally looks like a liquid. And I think in general, we're trying to get powders to move from one spot to another. If it's flowing like water, that's usually a good thing. That can have its cons in terms of you don't have the system sealed properly, but getting things to move is obviously a priority in a continuous process. And those are some ways that we can get that done. Certainly how you'd apply them is, again, kind of, it's case by case. There's not a magic bullet for everything. So that's in general kind of the comments on storage discharging. Dave, Jerry, before I get to the next topic, is there anything you want to add, Dave, from your perspective?
Well, all right. So one thing that's critical if you're going to use air to fluidize is dry air. Air dryers on your compressed air system are absolutely critical. I've been to power plants more than once where I'll see water spraying out of the line because, the dryers, are somewhat less than effective, especially on a test where you're using something on a one-off basis. But yeah, absolutely. And you should monitor dew point of your compressed air. Dew point monitors are something, an instrument that we've found that's really effective. You can get, temperature and dew point, relative humidity all in one measurement. It's 3 different IO points. Worth its weight in gold to get that monitored. The only way you know of a problem, there's 2 ways to find a problem. One is to measure it, and 2 is to find the effects of what happens if you let it go over time. You could make really big, I've seen snowballs of material in weigh bins, and that usually comes back to moisture infiltration.
No, that's a really good point.
Did you play the video? I didn't see the video.
You didn't? Let me see if I can get that going again, because it is pretty cool. But no, you're exactly right too. There's no magic bullet. There's a pro and con to everything. I think if everything's applied correctly, you obviously maximize the pros and minimize the cons. I will say that just in general, from a material handling perspective, in general, mechanical agitation is more efficient and better for larger particle sizes. Fluidization is usually more effective for finer particle size. So my personal opinion is fluidize when you can. Certainly have to have compressed dry air, but I will also say specifically the DSI, there's plenty of data and applications where mechanical agitation has proven to work just as effectively. And I know working with Luas on a past product, Jerry on a past project, showing how effective mechanical agitation is. It works. They all work. You just have to apply it the right way, is I think the best way to put that. So moving on to the next part of the presentation,
Mitch, we have a question. I wanted to just add to that real quick and just say that, in terms of, I know we could go down a rabbit hole in itself of fluidization and vibration, all that stuff. There are different kinds of fluidizers, vibrators, et cetera, et cetera. So to me, that's another thing that, people are looking at. Do I have the right equipment, for fluidizing and preventing these, these issues? Certainly that's a deeper subject matter you can go into, and there are a lot of different options out there, because, having it and then understanding, do I have the right version of that installed, is obviously, don't overlook that. Just because you have it doesn't mean it's the right solution for having fluidization or vibration. As we kind of talked about offline too, I think another important thing to make sure is that a lot of times those settings get put in the field and set during the startup and commissioning and may never get changed. And that's something that end users can look to optimize on based on experience to improve flowability of products. And like you've alluded to and talked to, even, not all hydrated limes will necessarily flow equal. Certainly we've seen that with our own various products. So I think, that to me is one thing, is always understanding all the physical properties of a sorbent. If you're going to switch sorbent and run a test with a different one, they may, flow differently. My personal experience, even from sodium to hydrated lime, been able to take a system that, couldn't flow with hydrated lime because it was designed for something else, and change a few settings and been able to get it flowing, as good or if not better than what it was before. So those are settings in the field you can tweak. Someone from the audience had a question. I think that's a good one for you guys, is all those methods that you discussed about, proper discharging from the silo, I guess the question is, have they all been used in the field? And I guess, can you, what kind of criteria do you guys suggest that would dictate picking one versus the other?
Well, for one, I think if you're new to the industry and you're sort of working at a greenfield site, I would spend a little bit extra money and go through the effort of having a flow study done. There's a few different companies out there that do flow studies on the material, and they will give you really good recommendations on how to get material discharged out of a silo just with gravity. So we've had great success with really sharp angle cones for getting material out of bulk storage. Air and fluidization is great, and for keeping things moving continuously is probably the right way to go. But as far as bulk storage and getting material out of bulk storage, I would recommend something that you don't need mechanical means to get the material to move.
Yep, and I'd just like to add to that too, that I think any, I would say, responsible DSI storage design with hoppers. I mean, again, fine powders, you want to keep at least a 60-degree cone in anything you're trying to discharge vertically in these applications, just because anything really lower than that just tends to lock up and not be efficient at coming out of the bins. And certainly if you can go steeper, great. That just allows you to use gravity to your advantage more and more. Great point, Dave.
Have you guys ever come across a situation, because I hear this too, and this along these lines of, say, using Dave as an example, say, plant goes into an unplanned outage for whatever reason, tube leak, something like that, and you got material sitting in your silo. Have you guys ever come across a situation that you couldn't get material to flow, or is there a finite period of time that you say, I feel comfortable having material left in my silo, and then I want to make sure I get it out because I have concerns about being able to get it flow again? Or are you able to have the right fluidization, vibration, whatever design so that no matter what, you are able to get it to flow and sustain flowability?
I mean, we've had several incidents where material has stayed in storage for months. In that instance is we'll run our truck unloading dehumidifiers and blow in dry air over the top of the silo for brief periods of time just to keep that air above that airspace above the bulk storage dry. You don't keep it on continuously because that's kind of a waste of energy. You could do that. That would be a conservative approach. But we blow in dry air periodically just to keep the material from agglomerating.
Makes sense.
Yeah, I think the other thing I want to add to that too, so as far as maximizing, so I will say, just like in general, the benefit in general, when we're mechanically agitating a bin, it tends to compact the powders, in my experience. Whereas with fluidization, I think you have a little bit more flexibility in terms of keeping things moving inside of a silo. So like, it's specifically to a silo. Like if it's in the bin, obviously discharging from a bin, you have much smaller volumes. So hopefully you can just empty the bin and stop the refill cycles on these systems. But if you are, for instance, in a period where you're not having to inject, but you still have sorbent in the silo, having the ability to fluidize and just keep things from not being stagnant in the silo, you have more flexibility to do that with a fluidizing setup than you would with a mechanical setup, I think. I mean, would you guys agree with that? Does that make sense?
That's a good point, because you think your video with fluidization, whereas, kind of sending material in a multitude of direction, whereas vibration's only going to send it one way.
Exactly. Yeah. Yeah.
We had a good
I
question.
saw a question come through.
Yep.
About dew point, and I would say a safe number to target would be like a -20 Fahrenheit for dew point. That's probably a bit overkill. And so ultimately, for hydrated lime anyways, relative humidity is what matters. And relative humidity changes based on the temperature of where you're at. But in general, -20 degrees Fahrenheit is going to be a safe number for dew point to target.
Excellent. Excellent. So we're gonna keep the train rolling here, going on to metering and feeding. Just had a couple points I wanted to make sure we talked about here. So I think the biggest kind of debate in metering and feeding that I've heard recently is coming down to volumetric versus gravimetric control. And for those of you that aren't aware of that, let's talk about what those are. So two methods: there's volumetric, there's gravimetric. And fundamentally how these work, I have a graph here that kind of shows, and process-wise, how these are talking to each other. But volumetric basis is where a feed rate is inferred based on a feeder speed based on a prior calibration. So essentially, it's only your controller is only looking how fast the feeder speed motor is going. There's no feedback from inside the actual sorbent tank itself. You essentially calibrate the screw at or feeder to run at different speeds. You do what's called a can check, where you collect a certain amount of material in a set period of time, and you tell your controller, okay, at X speed, I'm getting X pounds per hour. On a gravimetric basis, there's additional components that provide additional process feedback and ultimately resolution into what's going on in the process. Gravimetric feeding is where feed rate is controlled based on a direct weight measurement in your vessel. So those load cells are picking up a change in weight in a vessel, telling that to the feeder controller, and that feeder controller is taking that input on weight change and adjusting the feeder speed accordingly. So it's a third data point, but it does make a huge difference. So let's just go into the comparisons between these two technologies. For the gravimetric, I have a graph here that shows, it's a little busy, so I'll walk through this. On the y-axis, we have our net hopper weight. On the x-axis, we have time. So in this section, what's called the gravimetric phase, that is where our hopper is full and we are feeding continuously and the tank is draining. So you see over time, the net hopper weight in the vessel will decrease at a fixed rate because usually we have a fixed feed rate that we're targeting. We're taking change in weight over change in time to get a feed rate. The controller is processing that. Let's say there's any upset conditions that might affect the rate at which the weight in the vessel is draining. Say something gets locked up, like a bridging effect in the hopper, or let's say there's air that's not properly vented that's impacting the feed process. All those would get picked up on the load cells. And then typically this will happen until we hit a low set point on the scales, at which point the system will tell the vessel, okay, vessel's close to empty, let's refill it. So the system will put more material in the bin. As we're putting more material in the bin, we exit gravimetric mode or loss in weight mode temporarily. And usually what happens during this time as we're adding weight to the vessel is our controller will tell our screw speed, hey, until we get to our top level set point, just feed at a fixed rate, because we've already calculated that fixed rate matches a linear line here. And then once we hit our top level weight, the whole process starts over again. And it's a cycle that repeats itself over and over and over again. Volumetric mode, conversely, because we don't have that feedback on the vessel, a refill is typically based off of a level signal. You have a high level in the vessel, you have a low level. When your screw is spinning until your low level goes off, at which point the system says, okay, let's refill again until that high level hits, then the process starts over again. It's very simple by design, right? And again, the speed at which we're feeding, I should say the rate is calculated off a screw speed, which if we have any upset conditions in the vessel, I mentioned air venting, I mentioned moisture content, bridging, material density changing. If any of those things are happening inside the bin, the volumetric setup is not picking up those changes. So what I'm saying here is that gravimetric is giving you real-time information, what's happening in that bin. Volumetric is basically saying, I'm assuming everything is going well inside that bin. And I think if we all know that we can get in trouble when we make too many assumptions. So I think from my perspective, as having worked on these systems for essentially my entire career, a gravimetric approach is usually worth the additional investment from a process feedback standpoint. I'll give you some examples of the advantages of that. So because in gravimetric, again, because we can real-time measure the weight of material in the vessel, we can acquire actual data on actual sorbent use for strategic planning. We can streamline our logistics because we have better foresight into how much material we're actually using on a minute-by-minute basis. We have better resolution on stack compliance. Let's say we have a quarterly test that fails. So in a volumetric system, the only thing you can go back and look at is how did my screw speed change? And if your screw speed has always been the same and all of a sudden you're failing at the stack, you're limited into how you can problem solve. With gravimetric, you have more information. You have the ability to track, did I lose feed rate? Did I get an upset condition in the process that affects my ability to remove pollutants at the stack? Because again, we're not injecting material, we're not removing pollutants, which means that's going right out the stack. Gravimetric helps us identify those issues. I will say gravimetric, because there's more control components and load cells and things like this, it does require a higher cost, but in the grand scheme of things, that cost is usually worth it when you factor in all the benefits you can get out of that. Before I go to the next slide, Jerry, I know this is from a loss perspective, this is a thing that you guys really hit home. Is there anything you want to add on gravimetric versus volumetric for the team?
Oh yeah, this could go I know there's more cost. I don't want to trivialize anyone's money. I just think that from what I've seen, the cost of implementing load cells is relatively, minor in comparison. Had any customer I've known that I initially came upon volumetric, they either converted their system to gravimetric or are in some phase of doing that. Because not only is this not, as you talked about, it's not just about measuring the feed rate to know how much you're feeding, but it becomes a diagnostic tool that should trigger an alarm to somebody to say, I'm having a flow issue. Running volumetrically, you kind of lack that information unless you're out there with a stopwatch and a can doing the classic can tests and done that enough to know that material flows differently depending, like night and day, so seen it
Hey,
time
Mitch,
and
can you
time
go
again.
back to the previous slide?
Absolutely.
So one thing I use as an end user and as a process engineer, remote, I look for the sawtooth pattern in the bin weight. I see, just the classic, shallow slope down, sharp slope up, shallow slope down, and it looks like sawtooth, and it's consistent. The distance between fills is roughly, it's a pretty good gauge for your injection rate. The slope of that diagonal down line is your injection rate, actual measured. But when you start seeing like heartbeats or, squiggles, what that usually means is your bin isn't breathing. And I'll get to that in a few slides. But ultimately, if the bin is not at atmospheric pressure, you're not measuring the weight of the material. You're measuring the force of the pressure.
Oh, Dave, it's kind of like we coordinated this a little bit. I definitely wanted to mention, as it relates to feeding, and Dave's going to touch on this later on the next slide, but air venting cannot be underestimated. This can totally screw up your entire feeding process if you don't respect this. And what I'm showing is a cutaway of a rotary valve. On the top side is an atmospheric bin. Usually on the bottom of this is a pneumatic conveying system. Very common setup in dry sorbent injection. And at the end of the day, air is going to follow the path of least resistance. So if we have pressurized air on the bottom of this airlock, it's natural that some of the air is going to try to leak past this rotary airlock. And these rotary airlocks have very tight tolerances to prevent that. That's why it's called an airlock. But these are also wear components. And over time, these vanes can slowly wear away, which increases the gap in between the housing and the rotor. As the gap increases, that allows more air to seep by, which if air is seeping by in higher enough volumes, it can get into the atmospheric side of the weigh bin and hold up material, which can significantly reduce your feed rate capacity, or it can stop you feeding altogether. And that's why I say here, if not vented properly, this air will interfere with our feeding process, whether we have gravimetric or volumetric. If you have a gravimetric system, you'll be able to see it a lot faster than a volumetric, I would add. And I just want to say, like, there are additional equipment and pieces that you can add to assist with making sure the air is being directed to the proper paths that we want away from our material. It's worth it. It's an additional investment, but in general, it's usually worth it in the form of process reliability. So that probably goes right into the slides that Dave's going to be talking about, filtration. Dave, you want to take it away?
Thanks, Mitch. You're going to have to move slides for me because I'm just talking here.
You got it.
All right, so this is something I say to every plant system owner. I try to harp on it almost every time we talk DSI. And I hate reading slides, but I'm going to read this line because it's critical. Every DSI system has to breathe to operate properly. And what's that mean? That means every molecule of air that we push in to get the material moving has to be filtered and vented out of the process. Everything is operating at atmospheric pressure, right? So when you're injecting air to fluidize material, the only way you stay at atmospheric pressure is if all of that air that you're putting in is instantaneously vented out. So As far as bulk deliveries, that's filtered at the top of the silo on the bag house. That's pretty straightforward. There's some debate there as far as whether that needs a fan to pull suction on it or not. We've gone both ways with that. That's kind of, I'm not going to say not important, but it's, I'll say less critical to actually venting the equipment, the material handling system below the silo storage. So sources of air going into the stack up, whether it's aeration, whether it's weigh bin filling. Sometimes you'll have like an air slide pushing material into the weigh bin. A lot of times you'll see seal air on rotary valves for the one that's actually measuring the loss in weight. And then like Mitch was talking about earlier, injection air leakage. So that bottom rotary valve where it's feeding into the injection line, there is going to be some air that comes back by design. That's just the nature of how this thing works. And there are 3 different design philosophies to deal with venting. So next slide. So one method is you just vent everything near its source, right? So you have air going into the weigh bin, which are those skinny bins with the sharp cones on the bottom. You can put a filter on the top of that and vent it right there. And then at the bottom of the stack up, you have what's called a vent hopper, and that's where you're venting off that bottom rotary valve. That bottom rotary valve is under pressure, and that is that rotary valve is subject to pretty significant wear. Just as a side note, it's money well spent to chrome those bottom rotary valves, 100%. If you don't chrome those bottom rotary valves, the ones that are under pressure, they will wear out fairly quickly, and you'll be replacing them within a year, probably within 6 months if you run pretty significant run times. So method 1 is you vent everything basically at its source. Method 2, you can tie your vent hopper with a vent line into your weigh bin and vent your weigh bins and keep your silo storage area separate. And the advantage there is you're keeping your truck unloading, your bulk unloading separate from your loss and weight process. Method 3 is, and the idea here is to just tie everything back to a single bag house on the top of the silo. We've gone both ways with it, and there are pluses and minuses with those 2 approaches. But let me just say, don't use method 1.
Dave's stamp of approval. Go ahead, Dave. Sorry.
All right. So there are 2 different types of filters that are associated with the process: cartridge filters and bag filters. So cartridge filters, think about your shop vac and the pleats that are on one of those filters on the inside of your shop vac. If you run that thing every so often, it will pack. In general, one lesson that we've learned the hard way is that cartridges will pack, and pretty quickly, a cartridge that has a whole lot of surface to air, air to cloth ratio, that ratio goes away once it's packed with material. Then it just becomes a really thick bag. For my money, I think it's worth the extra expense to put in bags. Bags are easier to pull, they stay cleaner longer, and the air to cloth, in my opinion, is somewhat of a myth with cartridges.
And just to add to that too, I think, and I actually think you're gonna hit this on the next slide too, Dave, but the trade-off with the bags is definitely you're not getting as much filter area in a same compact space as you do with a cartridge. You probably can see that on the slide here, but to Dave's point, that works if you can continuously clean the cartridge, which obviously if you're looking at the pleats here can be a challenge, especially if you get moisture in the system. That just adds to making it really difficult to clean. Go ahead, Dave.
Yeah, so some of the other lessons that we've learned on the bleeding edge of this technology, if you don't have enough energy in your pulse air, you can keep pulsing all you want. It's not going to do any good if you don't have the energy there to keep the material off of your filter. So ensure you have enough force there. Vent lines. So the idea with vent lines is that you make them oversized for the amount of material that is going to be entrained in that air. So what you're looking for is material to drop out and go back to the process vessel below, but let the air go up to where you're ultimately going to vent that air. And so you want that vent line, if it has to be sloped, and there are going to be some spots where it's sloped, you want it to be at least 60 degrees, and a sharper angle is going to be better. So make it as sharp as you can. So he's got a little animation there.
Oh,
and
sorry,
then two more. No, you're good.
Okay.
Keep going. So the next 2 points are pretty important also. Only use the air you need. So what does that mean? So I can't tell you how many times I've heard about operators that come through on their walk downs and they see something they don't like. They'll put seal air and they'll take the setting at like 15 PSI and they'll start to turn it up 20, 25, 30 PSI. And then, you know, from their perspective, they're used to water pumps. And if there's something that looks like it's a leak, if you crank up the seal water on a slurry pump, you're going to force that leak to go back in. Well, in this case, if you crank up the pressure on seal air, what you're going to do is bust the seal, and you're going to make that leak much, much worse. So only use the air you need. And that also goes for fluidization. You know, we've had a couple different approaches on this. And if you have, let's say, constant fluidizer, sort of like, think of like a fly ash silo where you're constantly blowing in air at low pressure. That's going to be a really high volume of instrument air that's used to just keep it fluidized constantly. Another approach is to use a short burst of high pressure air just for like a split second, less than a second, maybe every 15, 20 seconds. And what that's going to do, if you remember from the video, you pulse it and it sort of puffs up, and it's going to keep that air in train for a while before it de-aerates. So you can do that and keep material fluidized with a whole lot less air. And what that's going to mean for filtration is that there's less air to filter and less material to deal with. And one final point is, and we've sort of learned this lesson the hard way too, is if you have a really fast wave in fill, that's going to stress filters on the roof of your wave in. So if you're taking and putting 3,000 pounds into a wave bin in 15 seconds, all that material that's rushing in displaces the air that's in the bin really quick. And there's things you can do to slow that down. You want the fill cycle to be roughly 60 seconds is a good target to have there. You know, you're going to be in volumetric mode for that 60 seconds, but it's a good balance between a brief period of not in loss and weight mode versus keeping your filters clean. Clean filters are definitely worth their weight in gold. Once you have that filter clogged up, if it's a cartridge, the only thing you can't even really pull it out, and you can knock it out and put it back in, and you might get some runtime. Ultimately, that's not worth it. You just replace it. That's the only way to really get it clean. You're not going to really get it clean unless you just replace it.
And just to kind of illustrate that, just to tie that back together, I'm going to go back a couple slides just to show on that sawtooth graph what we're talking about, which hopefully right here. Okay, so what we're saying here is the faster this is, the more vertical this is, the more taxing you have on your filters because you have more instantaneous loading hitting your venting mechanism. If this is a little longer, you decrease the loading on the filters, but the trade-off is you're in volumetric a little more. In the grand scheme of things, probably an okay trade-off, especially if air is being vented properly, to be in volumetric a little more to make the system more less burden on those filtration devices, but that's ultimately what we're talking about, is this phase right here on the wave in fill cycle. So just to put a picture to that concept. Sorry, Dave.
Thanks, Mitch.
Go through all these
Where were we here?
We're right here.
All right, here we go. Dilute phase. So DSI is a dilute phase pneumatic conveying system. What does that mean? So we're using air to move the material. It starts off at the highest pressure right at the discharge of the blower, and as you're moving down the pipeline, Bernoulli's equation always rules. You're moving from high pressure to low pressure. There's dilute phase and there's dense phase. Dilute phase means there's a whole lot more air than material air. That's typical for DSI systems and other material handling. So with dilute phase, there's less attrition on the material. You're not going to damage the material as much. There's less forces there. With dense phase, it's almost like a slug flow, and that's typical for like a fly ash handling system. That's not what we're going for here. With a dense phase system, you probably would have to inject air along the injection header to keep things moving, and the industry in general has gone to a dilute phase approach. So if you are a nerd, sort of like me, I've gone through and done these handling calcs where I try to predict what the header pressure is going to be. And in general, a good rule of thumb is that you need a pound of air to move a pound of material.
And if we're not moving, I think that's the important thing just to emphasize, is that air is the motive force. And if we're not moving any air, we're not moving any material in general. So let me, if I could just add a couple more comments here, Dave. So I wanted to emphasize that this is not something that's, I'm going to call it intuitive as it relates to operating the actual conveying system of these DSI system processes. So important fundamental concept is that we're operating based on a pressure differential, which is finite, meaning there's only so much we can work with. And our goal is that we're trying to balance the air plus the material in the line. I'm sure everybody that has worked with a DSI system or a pneumatic conveying system before has been in those situations where if you're not making rate, well, let's crank up the blower because we're obviously not getting enough material there fast enough. Well, that's not intuitive, but that's not necessarily true. Again, we can only put so much air plus material in a pipe because there's only so much pressure differential we're working with. So as we're adding air to that pipe, we're increasing the differential in that pipe, which actually is decreasing the amount of material we can put in the line. So I have a little chart here that shows kind of the delicate balance in these pneumatic conveying systems, as far as certainly we need a certain amount of velocity to pick up the amount of material once it actually enters the convey line. So we do have a baseline amount of air we need to at least entrain the material in the line. The differential pressure is going to be dictated by rate and distance. And with a certain amount of pressure, we can only go a certain distance and at a certain amount of rate. So like, let's say if we have to increase our rate and our pressure differential is 10, 11 PSI, we just can't get there. What's the mechanism? What's the lever we pull to potentially increase rate in that scenario? We increase the convey line size. What happens when we increase our convey line size? We decrease the differential pressure. That means we can put more air plus material in that line. So just one simple test. We do this all the time when we're looking at optimizing conveying systems. The first thing to look at is just let's watch our back pressures. And I say a gauge here. What I mean is watch your pressure feedback, whether it's a gauge, whether it's a transmitter, however you're doing that, the pressure gauge is going to tell you how well you're doing with your conveying. What I mean by that, let's do the Goldilocks test. So if that gauge is holding steady, that typically, and while you're changing rate, that implies that you have much more air to material in the line, which means you can probably back off on air. If that gauge or that transmitter is bouncing all over the place, a couple PSI, that usually means that your material is your rate limiting step, and you probably have too little air in the system, because that bouncing wildly aspect is indicating that you're maybe getting some material fallout, and the material is kind of falling out, picking up, falling out, picking up as it goes down the convey line. The Goldilocks approach is that you want a little rocking needle. You're never going to have a perfectly steady pressure reading on a pneumatic conveying system, but if it bounces half a PSI, 1 PSI, 1.5 PSI, it usually means you're pretty balanced on your air to material ratio in the line. And I think Dave, myself, Jerry, anytime we're working with our end users on optimizing the conveying process, we always start at the blower, because we only want to use the amount of air that we actually need to do what we need to do. Just going back to what Dave said in the previous slide, we try to use the lowest amount of air as possible to get the material from point A to point B, because that reduces our differential pressures. That allows us to put more material in the line, which means we're increasing our feed rate capacity. That means we're slowing the wear on wear parts like rotary valves, right? If we're subjecting our rotary valves to 10 PSI continuously, well, they're going to wear a lot faster because it's under a lot more burden versus potentially subjecting it to 4, 5, 6 PSI continuously. So making sure blower optimization is being done in your process is critical. That's why I think all of us on this call, when possible, make sure you have a VFD on those blowers. Those VFDs on the blowers allow for real-time adjustments in the field that you just don't have with a motor starter that's on or off. That's one thing I wanted to comment on. Dave, you want to? Sorry for stepping on your toes there. You want to take this call?
So yeah, you're all right. I mean, there's a couple other points I'll add on that. So in general, what we use for creating injection air are positive displacement blowers. This is a pretty classic animation. It's not really an animation. It's just 3 still shots that demonstrate when the 2 lobes rotate into one another. You know, it creates the motive force that pressurizes the air and pushes it on down the header. One of the things that I wanted to speak to with this is the fact that if you look at that, there are really, really tight tolerances between those 2 rotary lobes. And if you don't have enough air going through there, which that can happen if you're throttling on the suction side for some reason, it's going to overheat. When it overheats, those lobes, those lobes will expand a little bit, and what you're going to end up with is a wrecked blower, and you're going to be buying a new one. You can rebuild it, but for my money, it's almost not worth it because you're going to have a lot of damage in there also. But on the other hand, as you increase material loading in your injection header, the amount of force that these things are pushing out is going to increase. So if your pressure increases as you add more material into the line. AEP's approach, what we do is we set a constant speed for the blowers. We look at what we perceive to be our worst case, highest injection rate, and we apply a safety margin there, and that's where we set our speed. I think some folks that are probably on this call will tell you that you should put a VFD in, which will allow you to change the speed of these blowers in real time, and you can speed them up, slow them down. For my money, usually we have pretty big motors on these things, which means the VFD is going to be a very expensive component. In my mind, there's other parts of the system that require a certain set flow that are coming through there. We don't think the VFD is worth it. Other people do. It's a difference of opinion. I think you can have success either way. Next slide.
Absolutely. Yeah, I should say that 150 or 100 or those types of horsepower VFDs definitely get expensive, which is definitely plays into the equation for Dave and AEP for sure. We'll just go over the slide real quick. This is a slide I added, and this just again emphasizes that concept of leakage is important when it comes to maintaining the reliability of the process. And vacuum systems, this is not a problem, which probably some people watching this presentation use vacuum systems for their fly ash systems, for example. But a dilute phase pressure system where we have a pressure differential at the bottom of our rotary airlock just creates issues potentially with feeding, and it must be addressed. And I highlight the airlock vent hopper here because that is a vent hopper is something that's usually put in between the actual metering device, and the discharge rotary airlock to just better allow a path for that leakage air to go to a different location rather than impacting our feed process. But just want to emphasize that if you guys are having issues with potentially loss of feed rate capacity, one of the first things I look at is blow by or this rotary airlock leakage concept, which is common in every single dilute phase pressure system in the world. Frankly, this is not a new concept, so you're not alone. Moving on to injection air design, this back to you, Dave.
All right. So, so the system resistance is governed by basically two things. One is your splitters and your distribution, but also the distance that you're having to convey. So if you want to minimize your header pressure, you want to put where the material enters the line as close as you can to where you're injecting. Now, obviously, if you can't get trucks in and out of where you're at, it doesn't do you any good, right? So that's what I mean as far as logistics are concerned. So get the silo as close as you can. We size our systems to stay within a 3,500 to 5,000 feet per minute velocity range. If you're under 3,500, you're risking going below what we call saltation velocity, which is the minimum velocity required to keep the material entrained. So you have to stay above that. If you're going above 5,000, that's going to be that's adding resistance, and that's going to be pretty wasteful. So what we do, like I said before, we design for the maximum injection rate with some safety associated with that. And I think there's a couple more bullets. Yes. So this is key. So as you're at that higher injection rate, you're at the higher header pressure. And so as that pressure goes up, the carrying velocity of the air goes down. Just think about PV equals nRT, right? The ideal gas law. Pressure is going to, higher pressure, lower velocity. That's always the case. And so what happens is if you have a marginal system, and we've actually seen this, if you have a marginal system and you can't carry any more material, what's going to happen is the material is going to drop out. Your header pressure is going to spike, and it's going to immediately go to the safety release setting on your blower package. Seen that many times where you get into upset conditions. If you see a spike, what that means is there's no material moving whatsoever. And you probably need to shut down, stop adding material to the header, and let the blower catch up. And at that point, you got to back off what you're adding once you get it down to what is going to be your air-only pressure. Next slide. Oh, yeah, I'm sorry, one last thing. And I even bolded this one because it's so important. You need to dehumidify the inlet air. We have learned that lesson the hard way. If you're starting with a new system, just go ahead and figure on that as part of your budget. Why is that the case? When you're handling hydrated lime, in general with chemistry, chemicals want to go to their most stable form, right? So when you make hydrated lime, you're starting with calcium carbonate or limestone. Limestone is what they pull out of the ground. That is its most stable form. When there's humidity in the air, the humidity acts as a catalyst for the hydrated lime. When you add it into an injection header, it will react with the CO2 just from ambient air. And so the temperature is temperature-driven, moisture-driven, and also velocity-driven. So what the idea is if you take away one aspect of that equation, which is the easiest thing to do is to take away the moisture, you can prevent that from happening. I know there were several systems in the past where the material would enter the line, and after about a week, or in worst case scenario, a shift, you will get from a full pipe to what you see here, which sort of looks like a powdered donut on the inside of the line. And so once you get to this, something that looks like that, what you have to do is you have to pull out the pickup tee and rot it out, go to the other line, and put it back in service. And switching back and forth like that is what Mitch was referring to earlier as a maintenance nightmare. You don't want to be there.
Yeah, I think I wanted to add to this too, because this is a slide that I borrowed from a presentation that Chad Donner has given, not only DSUA, but all other sorts of presentations in the industry. But there's certain components that we add upstream of the blower to drive this moisture from the air. There's pre-chillers, there's dehumidifiers, which are typically desiccant wheels, and there's heat exchangers. And we kind of show what each one of those unit operations is doing. But in general, the design criteria that everyone's kind of honing in on as we get more and more information from real world applications is 8% relative humidity. If you can stay under 8% relative humidity, this equation that's shown on the screen of converting to this calcium carbonate, which creates this effect, is significantly reduced, borderline eliminated. And this graph here, which is what I took from one of Chad's old presentations, was kind of showing how the air that's passing from ambient to ultimately the blower inlet is impacted as it goes across these conditioning components. So, we're showing temperature, moisture, and dew point from an ambient condition. Once it goes over the chiller, it's really brought to saturation. And then once it goes through the chiller and over the desiccant wheel, which really drives off the moisture through a desiccant drying process, you can see how we add heat, but again, it drives off moisture almost entirely, so that when we have a hotter, or I should say warm gas that has no moisture in it, our relative humidity is near zero. So that's how we accommodate that real world in the field. Dave, you want to walk through what a typical dehumidification system is here?
Yes. Yeah, well, you sort of stole my thunder there, Mitch.
Sorry.
You got the gift of gab. Well done. So dehumidifying skid, it's a skid mounted system, sort of a plug and play deal. So there's two main aspects of it. There's a cooling coil and there's a desiccant wheel. One thing that you ought to consider, I know not everyone does this, but you probably ought to consider putting in a post-cooling coil after the desiccant wheel. Injection blowers are happier with cooler air entering them. A post-cooling coil will greatly reduce that air temperature, and it will make your injection blowers happy. A process air booster fan, what that's going to do is eliminate resistance on the suction side of your injection blower. So you want the resistance happening downstream of the blower, not upstream. You never want to have negative pressure going into your injection blower. And I think I've referenced this before, but you want to monitor temperature, dew point, relative humidity. There's a single instrument that'll do that. It's made by a company called DSI. I'm happy to provide information on that if anyone's interested. But it's a single component that monitors all three in real time. Worth every penny. Can't stress that enough. If you can't measure it, you can't control it. If you can't control it, it's not going to be, you're sort of flying blind, right? So this is what the process looks like for dehumidification. So the line on the bottom is the process air. So it starts on the right, works its way across, goes through a pre-filter. It sort of looks like your furnace air filter at your house. And it goes through a cooling coil. And so that has either glycol or refrigerant, also like your house air conditioner, right? But bigger. And that's sized based on the size of your injection blower. So once it goes through there, you're going to have condensate coming off of it, and it's coming out as really cold, but it's completely saturated with water. So you've gone to the dew point, and you've gone your post-cooling through a dew point, right? So as once it comes off the cooling coil, it goes through a desiccant wheel, which is that material like in your shoes, those little packets. Those are silica gel. That's a desiccant. It pulls moisture out of the air. I don't know that it's exactly silica gel, but it's something similar to that. And it's embedded in a wheel, and the wheel has two chambers for air to pass through. One is the process air. So that wheel is turning continuously. And on the one side, you have process air going through. So coming out of that, it's heated. And then it goes through a booster fan and it goes out to the injection blower. So the reactivation air on the top also has a filter on the front end of it. And then it has an inline heater. The heater is what's blowing through the desiccant opposite direction. And that is continuously recharging the desiccant and removing the moisture out of the desiccant. And so when you can put your hand on the discharge of that reactivation air blower, and you're going to feel warm, moist air coming out. Next slide.
Hey, Dave, one thing I just wanted to call out specifically, because, is, the cooling coil upstream of the dehumidifier. I think the earlier generations of the DSI systems in the utility market, I know we all tried dehumidifiers and with mixed success. And in some cases, the dehumidifiers alone kind of made problems more problems than solutions, I guess. But consistent with what you've been saying, and I think it was just important to note that, that cooling coil, as well as Chad has presented and talked about, you guys are all now about talking about relative humidity, and that, that cooling upstream of the dehumidifier coupled together helps control that relative humidity, make the dehumidifiers more effective. So I thought that was an important distinction, just to make sure people understand.
So Mitch, go back to that slide, actually.
Which one?
So what I talked, right there. No, the one with the process flow on it.
Okay.
Yes. So when I talk about a post-cooling coil, I'm talking about basically right there where he's hovering, probably after the bypass loop. And so what that would do is when the process air goes through the desiccant wheel, it gets heated. And so if you put a post-cooling coil in there, you're going to cool that air back down to some nominal temperature, still above, well above relative humidity, to where we're not going to be at, hovering at 8%, but it's also going to make your injection blowers happy.
Exactly. Yeah. So that post-cooling coil is primarily there for keeping the blowers happy. Because again, as we go through the blower, we're pressurizing, so we're adding heat. So we're going to get a temperize on the discharge of the blower too. So I think one of the things we're learning is that it's this unique balance between not only drying, but also controlling the temperature, because the temperature is impacting your relative humidity, and relative humidity is the factor that's driving that reaction that we're all trying to control. So even though this has been around for 20 years, we can still learn, right?
Right.
So I think the last
we only
part
have a couple minutes left.
Yep. Yeah. We only have a few slides on duct distribution. David, I just want to emphasize that obviously splitting is an important part of this, and especially in bigger applications, we want to split and maximize the use of the sorbent to optimize the cost of the material. This is two-phase flow. This is air and sorbent in a pipe. So it's not as easy as it sounds, because material doesn't necessarily want to go the same. It's not directly correlated to where the air is going, but it's similar. But it can also be difficult to kind of observe, because back pressure is like, how do you monitor where the sorbent is going? It's a challenging industry, but we definitely have some splitter design considerations. Dave, do you want to walk through these quick?
Yeah. So splitters, in general, what's going to be the most successful is a resistance style splitter. So what that means is we put an orifice on each of the branches. So sort of like with a manifold, if you have half the flow, half the cross-sectional area of the line coming in for each of the branches coming out, you're going to get, in general, really good distribution through each line. So that's something we do with manifolds and water flow also. A couple other considerations to have. Number one, you really want at least 10 straight pipe diameters going into the splitter. And if you can, use a single splitter, but I wouldn't use any more than two. I've seen some approaches where they do two-way splits for like 5 levels of splitters, and you're really asking for trouble if you go down that path.
That's good. And then I know we have, this is the last slide. We're going to talk about induct dispersion because I know Dave and AEP are doing some pretty cool stuff with that. Go ahead, Dave.
Yeah, so for dispersion, our approach, and we've demonstrated it several times, our approach is to use our ammonia static mixers. You can put these anywhere in the process. For us, we already have these, so we're going to use what we have and make it work to our advantage. So you inject basically on the upside edge, and what happens is, go back to the other slide. What you create is basically a vortex that goes around the delta wing, and the delta wing is really good, and we've got videos of it that show it, but it really spreads the material out across the entire cross section of the duct, and that is going to be your best bang for your buck as far as getting material across the entire cross section. Next slide. So when you're looking at a static mixer that's like around, that's like I think 10 foot wide in the duct, you want to target approximately what that red box is. The bottom part of that disc is where you're going to get the material to spread everywhere across them. And I think that's the last slide.
That's right.
Probably been talking a lot, and I've only seen a couple questions come through.
No, we've had, you guys have done a good job answering the questions. And I, appreciate you guys. This is could be a very deep rabbit hole. And, I think it was probably challenging to try and get enough, condense the material appropriately down to fit the time constraints, because could be a huge talking point. So I appreciate that for you guys. And certainly if more questions come through, and if folks are interested in even a follow-up session, I know some of the things that we talked about offline too, that we could always get into, that's kind of near and dear to end users. We've talked about, the value of a screener box, what to look for. We've talked about silo sizing. What do you do if you already got a silo and it's too small for your liking? You guys did a great job talking about the rotary airlock, but you could dedicate a large chunk of time talking about rotary airlock 101, materials, maintenance, designs, there's deeper discussions in that, even airlocks versus screw feeders as your primary means of controlling your dosage rates. The piping from the types of pipe, the connections, hose versus carbon steel versus other materials of construction, bend radius, there's a whole area there. You could dedicate probably 90 minutes to conveying air chemistry, as we've kind of talked about, lessons learned on that, as well as even splitters. Even what to do in terms of cleaning lines and elbows. We touched upon instrumentation. The dew point monitor, Dave, I appreciate you talked about that, because that's not common out there. And I'm sure we could extrapolate a little bit more about the value in that and the challenges of silo level instrumentation. So there's a whole lot of other topics I'm sure we could talk about even more. That would be valuable. If anyone's ever interested or has questions on any of those specific topics that we weren't able to get into today, or anything more in depth that we did get into, send us an email through the DSUA website. The recording should be available here within a couple of days or so, and feel free, we'll distribute it. Feel free to watch again if anyone comes up with questions. I'm always happy to send it to Mitch and Dave and let them field it. So thank you guys again, and we'll be talking to you guys soon and catch you on the next webinar. Thank you, gentlemen.
Thanks, Jerry.
Yep. Take care, everybody.